pulsed DCIB measurements, millimeter wave active load pull, W-band noise parameters like Nick just spoke about today. His current emphasis is on semiconductor device characterization and measurement methodologies for advanced modeling and measurement-based design. He's a senior IEEE member and serves as the section vice chair of the IEEE Foothill, California section. He holds bachelor's, master's, and PhD degrees in electronics engineering, and has previously worked in Turkey, Japan, and the Netherlands in the field of high-power RF. He has design experience with high-power devices, amplifiers, and transmitter systems. And with that, I will mute myself and hand it over to Osman. Osman, the floor is yours.
Just let me share my screen quickly. Can you see it?
Yep, looks great.
Okay, that's great. Yeah, good morning from Los Angeles, and thank you very much, Steve, for the introduction. As he mentioned, I'm going to talk about the load pull concept. It's not too much detail, so don't worry about the equations and other things. I will show how we apply load pull, active load pull, and hybrid load pull, especially for high power cases. So, and after my presentation, as Steve mentioned, you will see some great applications. Today, we know that high frequency applications, W-band, D-band, E-band applications are more accessible, and that's why demand from these technologies are also getting, let's say, difficult, like wider bandwidth, more efficiency, more gain, and other things. And for all these things, we know that large signal analysis is really critical and important, and it's a kind of necessary, as the presenters of the modeling session in previous session mentioned. They are getting more important, and so let me summarize quickly what we are doing. So we know that with the power case and efficiency case, we know that output power, efficiency, power gain, and linearity is a function of biasing input signal power, input impedance, output impedance. And we know that this function is not linear, right? Especially for large signal cases, it becomes really complicated, and that's why we need a load pull analyzer. So what does that mean? So you have a device here, it could be a device or a complete design. If you manipulate the load impedance and measure the results, measure the parameters, efficiency, power, gain, and other things, you have lots of information about your device, and it gives you a very good start for modeling, for design, or for evaluating reliability of your technology. And that's why it's called load pull. So you load your device and you pull the results, and then you get a lot of information. And the classical method, electromechanical impedance tuners, these are quite useful for lower frequencies, but when you start talking about higher frequencies, we know that if you have more insertion loss between your transistor, your DUT, and the tuner, you can control smaller areas. So this is a very nice measurement example here. For example, at the tuner reference plane, which means here you can cover blue area, so which is more than almost 0.9 gamma. If you have 1 dB insertion loss, you can cover this red area. If you have 3 dB insertion loss, you can control really small area. And for high frequencies, we know that all the components are very lossy, right? Including the probes. If you look at the probes, they have more than 1 dB insertion loss. If you have any other thing between the tuner and your DUT, you can control really tiny area, which means that you cannot get enough gamma to see to observe closed contours for maximum efficiency, power, and gain. So that's why we need a new solution, which is called active load pull. In this case, we sample the signal after your transistor, and it's the A2 signal, B2 signal. Then we have a digital control system here since we know exact phase and amplitude of B2 signal, a computer control system can generate a suitable A2 signal to generate any load impedance here. So it's an artificial load, but it's on us, so we can control any gamma by injecting correct A2 signal. And of course, the critical thing here is the power. When you have enough power, you can go any gamma, even one and larger than one gamma. So in this case, there is no problem covering the Smith chart because you can go any region on the Smith chart and you can close your efficiency, power, or gain contours easily. And I will show some examples. This is even possible at very high frequencies. So this is how we apply it. So this is a VNA-based example. In this case, your duty is here, and as you see, there is no tuner here. We don't need tuner for active load pull. And for this example, we use one of the signal synthesizer in the VNA, and we apply suitable A2 signal to control the load impedance that duty sees. So this is the easiest application. As you see, it has less components, and you always, as you remember, if you have a vector receiver-based load pull, you always have calibration at the duty reference plane. And depending on the calibration, of course, you can have at the transistor level transistor intrinsic transistor level plane or probe tip level plane. That depends on your calibration, but it's a vector calibration, so that's why you have precision control here. So and the second concept, hybrid active load pull. So in this case, we have a tuner here, and this tuner is used for pre-matching. So this is a very nice example how you can go very high power for very high frequencies, because we know that, as I mentioned, for the active load pull, if you go back to the previous one, so in theory, you need a minimum 5 to 7 dB more power than your duty. So let's say if your duty is 1 watt, in theory, if you include also the insertion losses, you need, let's say, 10 watt driver amplifier here to go any gamma at your DUT reference plane. But if you think about the millimeter wave load pull, very high frequency load pull, the cost of this type of driver amplifier might be really high. So that's why we have a second solution. Still, it's active load pull, but you have a pre-matching tuner here. So let's say this is a 50 ohm line. Sorry, from amplifier to tuner, it's a 50 ohm transmission line, but your tuner, for example, can bring it to 50 ohm to 10 ohm or 5 ohm, which helps impedance transformation for active load pull. So in that case, you need really less power. I have a high power example here, but you can definitely apply same thing to higher frequencies. So let's say if your device is 0.9, if your device needs 0.9 load gamma at 100 watt, and if it is a 50 ohm system, there is no pre-matching from your driver amplifier to your DUT, you need a 50 dBm plus insertion losses, which means almost you need a 1 kilowatt amplifier to drive your transistor. But it's not only the power is not only the problem. When you consider 1 kilowatt drive signal from here, standing waves might be really dangerous for some of the components here. This is a very important thing as well. And then if you think about the hybrid active load pull system, so let's say your tuner can bring 50 ohm to 5 ohm or 10 ohm. So in my example, it's 5 ohm. The same transistor, 0.9 gamma for 100 watt, you need only 41 dBm. So look at the power difference here. So that's why pre-matching is very critical, especially for high power and high frequency applications. So again, we can apply same thing to high frequency applications. And this is a nice example here. So for example, this transistor is measured at 38 gigahertz. P out is 1 watt, 30 dBm, and you can see here we can reach easily 0.8 gamma closed contours. Of course, the system can go higher gamma, but we got closed contours at 0.8 gamma here. So the second concept, so the previous ones are for VNA-based load-pull systems. And we have another solution for active load pull. It's called mixed signal. In this case, we generate a control signal using arbitrary wave generator. So here in this example, you see 6 different signal synthesizer, arbitrary wave generator, and you can control multiple harmonics. You can combine all the signals and inject to the device. So this is all active and all vector. So you can control, in this example, 6 different signals using a mixed signal load pull system. So how does that work? So the concept is the same. The only difference, we can generate multiple control signals. So if you think about source side, we can generate more A1 signal, for example, or if we talk about the load side, we can generate multiple A2 signals in one measurement sweep. So then you can control multiple impedances almost simultaneously. These are, of course, not at the same time, but very short timing, which means that it's really fast because in one power sweep, you can complete multiple impedances. You can run load pull for multiple impedances. Plus, you can use the same bandwidth for modulated signals, which means that you can apply modulated signals to your non-50 measurements, large signal cases. And here is one example. Since the system has wideband receivers and transmitters, signal generators, as you can see here, you can also save the spectrum. You can watch what's happening with your signal, including two-tone. This is ACPR for this transistor, EVM data. And if you want to learn more about this system, we have a very nice video on YouTube. I highly recommend checking that video. It's only 5-7 minutes, and it shows how it works. And you will see the measurement speed and the basic concept of mixed signal active load pull measurements. And let's switch to ENW band hybrid system. So in this case, we use VNA, and the critical difference here, as you know, you cannot control extenders, right? So they are kind of dummy devices. You just inject the power input signal, it multiplies, and you get the multiplied output frequency, and that's it. So you measure S parameters. But with this system, you can control the phase and amplitude. So we have a control unit designed by Maury here. We still have a frequency extender. We use a step attenuator for larger steps. So again, this control unit controls the phase and amplitude. But for larger steps, we use a step attenuator here. It doesn't mean that it's really slow, because again, it goes some attenuation level and just run. Then the electronic control takes the control and controls the phase and amplitude. So then it can apply active load pull. So in this case, you don't have to use a tuner, but again, we recommend using a tuner for pre-matching. But same system can be used only for passive load pull or hybrid load pull like this. The advantage here, you can pick any power amplifier to close your contour. So again, if you have a really high power DUT here, we can calculate roughly the insertion losses from tuner to your DUT, and we can calculate how much power you need to drive your transistor to go gamma 1. So that's the flexibility of the system. And again, it really depends on your device, because the main cost in this system, one of the main costs in this system is external power amplifier for very high frequencies. And we have some solutions for this. You can have narrow band or wideband solutions, of course. So this is one way to have hybrid active load pull system for very high frequencies, E band, D band, or W band frequencies. And again, tuner is optional here, but we always recommend to reduce power requirement for driver amplifiers. So this is one example. This is from our laboratory. In this example, we measured a high power device to test this system. And the concept is the same again. This is the control unit here, VNA. The signal, low frequency signal goes to control unit, then it comes to the extender. We have precision control here. Then it goes, it comes from this way. This is the step attenuator. We have a 5-watt driver amplifier for source and 10-watt driver amplifier. It's here for the load side. And again, with this setup, we can easily go more than a few watt control at duty reference plane, and the tuner is here. So in this example, for example, we didn't use a source tuner. Again, it's up to you. So this is an narrower wave, and one of the key components here, we have active down converting couplers, and this is a special design, especially for this type of setup. Then that's why we have a calibration at the duty reference plane, vector calibration, and all measurements are vector. So you have amplitude and phase information at the input and at the output. So at the end of your measurements, you will get a lot of information about your device. So this is one example. This is a smaller device. Unfortunately, we cannot show all the information, but after my presentation, you will see some high power applications. For this example, it's 80 gigahertz and P out is 15 dBm. And as you see here, we can easily reach 0.9 gamma with this type of setup. So again, this setup is for now. This is available up to 110 gigahertz. Hopefully, soon it will be available for high frequencies up to 300 gigahertz. But what about after 300 gigahertz? What are we going to do after 300 gigahertz? We have another solution for that. So in this setup, we still have a VNA. We have a control unit here. The key point here, as you see, there is no tuner and there is no external power amplifier. So our solution in this setup controls the extenders precisely. So we can, so it's of course it's our IP, our partner's IP. So it means that we can control amplitude and phase. Then you can apply active load pull. So we can control amplitude and phase of the extender. And then you can have, of course, active load pull at the duty reference plane. Here, people always ask us, how do we, so what is the limitation here? The power limitation depends on your extender here. The advantage of this setup, it can control any type of extender, which means that if you need a higher power application, you can talk to us or you can talk to your vendor and you can get a suitable output power extender. So of course, this means additional cost, but if you need this type of solution, there are some possible solutions. We can definitely talk. And this setup, there's no limitation about the frequency because it's up to extender. So if you have extenders up to 1.1 terahertz, you can apply active load pull up to 1.1 terahertz. So that's the advantage. So you can have wider bandwidth setup. So in this, in the previous example, one of the limitation again, since very high power amplifiers of the external power amplifiers, very high power external power amplifiers could be really costly. That's why I know some people prefer narrow band solutions, for example, only few gigahertz bandwidth solutions, then you can reduce the cost. But again, it's a solution we know in the market. There are wideband millimeter wave amplifiers as well. But in this example, again, we know that most of the extenders are quite wideband, so it can cover a wider bandwidth, but the limitation here, the output power of your extenders. So that's the limitation here. The good thing again, you don't need to have a specific extender. You can use almost all vendors' extenders. So here are some examples. This is 125 gigahertz example. As you see, it's reaching 0.7 gamma here in this example, and the output power is around roughly 0 dBm ish, 135 gigahertz. Another example, you can see it can go more than almost 0.9 gamma. The output power, where is that? Getting closer to maybe 3 dBm ish power. Another example at 250 gigahertz, the output power is around minus 5 dBm, but you can still have closed contours. So again, these are lower power applications. You will see some very interesting applications in the following presentations. So that's summarized. That concludes my presentation. I'm checking the questions if we have. I cannot see.
Doesn't look like there's any questions in the Q&A section, Osman. There's no public.
No, I see one on the chat box. Actually, it's from the previous one.
All right. Well, thank you very much. Thank you very much, Osman. And I'm amazed you did it in 22 minutes. So thank you very much for that.
Yes,
Osman,
last session, I didn't want to keep people here for a long